Hello everyone, welcome back to ACE Exams. This is Maath Alabdali, and today I'll be explaining waves motion for A-level physics. Okay, so what we're gonna do today is we're gonna describe and distinguish the difference between progressive, longitudinal, transverse waves. We're gonna define and use the terms displacement, amplitude, wavelength, period, phase difference, frequency, and speed of the wave. Every single term in these has a specific definition, so we have to know that. We also have to derive from the definitions of speed, frequency, and wavelength, the wave equation V equal to F lambda. And we have to select and use the wave equation V equal to F lambda, explain what is meant by reflection, refraction, and diffraction of waves, such as sound and light. So I'm going to explain all of this in this video. Okay, so all wave motions, okay, from sound wave, water wave, they're all disturbances which pass through a substance, apart from the electromagnetic waves. So a series of waves similar to those produced on a water surface can be generated in a long piece of rope which is fixed at one end and moved repeatedly at right angle to its length, as shown in the diagram opposite, which is, I'm going to show the diagram. So in here, that's the first example. Second example, waves similar to sound wave are produced in a spring coil which is fixed at one end while the other end is repeatedly moved as shown in the diagram opposite, so in this one, for example. And a pebble dropped onto a still water surface causes a vibration which produces concentric circular waves which spread outwards across the water surface. So for example in here, all of these are waves basically. Okay, so now it's time for definitions, very important definitions. Progressive wave, it's a transfer of energy as a result of the oscillation. Waves can be classified as mechanical wave and can be classified as electromagnetic wave. So for mechanical waves, they are the waves that transfers energy through a medium. Okay, electromagnetic waves are waves which don't need a medium to transfer energy. So for example of mechanical wave is water wave, sound wave, waves along a spring coil. They all transfer energy through a medium. However, electromagnetic waves, they are the waves on the electromagnetic spectrums. For example, gamma rays, X-rays, UV, which is ultraviolet, visible lights, infrared, microwaves, they're all radio waves, they're all example of electromagnetic waves. So waves can also be transverse and longitudinal. Transverse wave, which is basically displacement of particles, which is perpendicular to the direction of the energy transfer. Sometimes instead of energy transfer, you can write propagation. So displacement of particles is perpendicular to the direction of propagation. Longitudinal wave is when the displacement of particle is parallel to the direction of the energy transfer propagation. So example of transverse wave, the water wave, secondary seismic waves, all the electromagnetic waves are transverse waves. Okay, so they all have the same speed. Longitudinal wave, example sound wave, primary seismic waves, they're all longitudinal waves. Now, so these are the terms associated with waves. So amplitude, that is the proper definition. Maximum distance from equilibrium. You have to write this definition in the exam to get the mark. Displacement is the distance moved from equilibrium of a point on a wave. Wavelength is the distance between two successive points in phase. Period is the time taken for one complete oscillation of a particle, and frequency is the number of wavelengths that pass through a point per unit time. Okay? Phase difference is basically the fraction of a cycle measured in degrees between the oscillation of two particles. So for example, phase difference can be measured in degrees or radians. So for one cycle is 360 degrees or 2 pi radian. So for example, in here, the diagram above, particles at point D and point E are one wavelength apart, so they vibrate in phase with each other. And then the phase difference between the particles at these 2 points is 360. It's one wavelength, so 2 pi radians. And particles at point A and B, they're half of a wavelength, and they vibrate in anti-phase. And the phase difference between the particles at these 2 points is basically 180, or 2 pi divided by 2, which is pi radians. Now, the wave speed, which is basically meters per second, and this is basically the speed with which energy is transmitted by a wave. Okay, so the wave speed equation is basically v equal to f lambda. Okay, so we know that v equal to, wait, hold on, no, this is, yeah, it is right, v equal to f lambda, but we have to derive it. So we know that wave the speed is basically the distance divided by the time traveled. Okay, so the distance is a lambda, which is wavelength, divided by the time, and we know that time equal to 1 over frequency. So if we substitute that into the formula, we get v equal to lambda divided by 1f, and if we simplify that further, we get v equal to f lambda. Okay, so that's how simple it is. Very simple, very straightforward. So v is basically measured in meters per second, f is in hertz, and lambda is wavelength meters. Reflection, refraction, diffraction of waves. So this is an experiment that we have to know. So in a ripple tank, as shown opposite in here, may be used to demonstrate reflection, refraction, and diffraction of water waves. So the waves are produced by vibrating straight-edged bar that can be viewed from above. Okay, so in here, or projected onto a screen. And then the straight lines observed on the screen show the position of the wavefronts, and obstacles are placed in the path of the wave to see what effects are produced. Okay, so that's basically the ripple tank experiment. So reflection, we're going to look reflection, refraction, and diffraction specific. So reflection is basically the bouncing back of a wave from a circuit. Okay, so for example, in here we have, this is the wave direction. This is a reflector and this is water, and the waves are sent at an angle to a straight reflector, and angle of incident is basically equal to the angle of reflection. So in here, the angle between the reflected wavefront and the surface is basically equal to the angle between the incident wavefront and the surface. So the direction of the reflected wave is at the same angle to the reflector as the direction of the incident wave. Okay, so this is a demonstration in like a wavefront instead of a ray. And this is a demonstrate, like this is a ray. So in here, the angle of incident equal to the angle of reflection. So we usually draw a normal, which is perpendicular to the surface, and then the angle between the normal and the angle of incident is what we call the angle of the angle between the normal. The angle of incident is the angle between the normal and the incident ray. That's the angle of incident. And the angle of reflection is the angle between the normal and the reflected ray. And usually they are equal to each other. If they are equal to each other, then this is reflection. So in here it says, when a ray of light is directed at the plane, the angle between the reflected ray and the mirror is equal to the angle between the incident ray and the mirror. So sound waves are reflected in the same way. So in here it compares the angle between this incident ray and the mirror instead of the incident ray and the normal, which is perpendicular to the mirror. It's the same thing. They're both equal to each other. You have to the angle between the mirror and the ray is equal to the angle between the reflected ray and the mirror. Okay, that's what I mean. Refraction. Refraction is the change in direction and speed of wave as it crosses an interface between two mediums. So this is the proper definition of refraction. So in here, we got waves. They slow down in shallower water, and this is a flat piece of plastic. So a flat rectangular piece of perspex placed in the tray makes the water shallower, and as the wave passes over it, they are slowed down. So in here, that's another example of refraction. So when the water waves are incident at a deep, shallow boundary at an angle, they change the direction and the wavelength decreases. So this is because v equal to f lambda, and since the velocity increases, v stays the same, then the lambda must decrease, the wavelength must decrease. And this is also demonstrated using this example in here. So an array of light is directed at a parallel-sided glass block at an angle, it's also refracted. So in here, the light waves slow down, and so they change in the direction when they're passed from air to glass, and then from glass to air. So when they pass through the glass, they slow down, and then when they're out, they speed up again. Diffraction. Diffraction is my favorite. It's basically when wave front spread out after passing through a gap or aperture or around an obstacle. So you can either say gap or aperture. So aperture is just a posh word for gap. If you say any, you'll get the mark. So in a ripple tank, okay, plane waves are directed at a grabbed barrier are seen to spread out as they pass through the gap. So by varying the gap width d and the wavelength theta of the waves, it's seen that the extent of the diffraction effect depends on both the wavelength and the d, which is the width. So in here, you can see that when the gap d, with the width d, is large compared to the wavelength of the incident waves, then the diffraction effect is small, while in here you can see that there's a high diffraction because d is small, the width is small. So yeah, so the diffraction effect is greatest when the wavelength of the waves is equal to the gap, which is the width. So if this is equal to this, then there's a high diffraction. That's basically it. Okay, thank you very much for listening. See you in the next video. Make sure to stay safe and don't forget to subscribe to my YouTube channel. Bye bye.